So our next presenter, I'm sorry for messing you around earlier on, is Ruben, and he's going to present about some research on semi-probabilistic rules that he's been developing with Deltaris.
The voorzitter present.
Pointer?
Well, thank you.
Is this microphone on?
Okay. Oh, use this one. Well, thank you, Mr. Chairman. This talk is about calibrating semi-probabilistic assessment rules for assessing dike safety. And before I'll explain what is actually meant by a semi-probabilistic rule, an assessment rule, I'd like to acknowledge my co-authors, Mr. Ed Kalle from Deltaris and Professor Ton Vrouwenvelder from the Research Institute TNO here in the Netherlands. The outline of my talk is as follows. I'll start by giving you a brief introduction to the background of this research project. And I'll then explain what is meant by a semi-probabilistic assessment by contrasting it to the more familiar probabilistic assessments. Then I'd like to introduce the calibration procedure that we developed for defining safety factors, which are essential components of any semi-probabilistic assessment. I will then briefly go over a case study and end with some concluding remarks. You've probably seen this figure many times, the figure on the left-hand side. These are the safety standards that we currently use in the Netherlands. And quite often these safety standards are confused with maximum allowable probabilities of flooding. Well, they are probabilities, but they are not maximum allowable probabilities of failure. And I think it's important to keep that in mind. At the moment, our policymakers in Holland are contemplating a move towards new safety standards, a new type of safety standards that would be defined in terms of maximum allowable probabilities of flooding or maximum failure probabilities. Deciding on such maximum allowable failure probabilities depends on a risk evaluation. And there's a talk at this conference by Mr. van der Most about the policy proposals that are currently being discussed. Of course, if we move towards a new type of flood safety standard, we have to be able to evaluate or test our levees against these new types of safety standards. And that basically means that our current methods could no longer be used. And that's where the WTI 2017 project comes around the corner. Its objective is to facilitate or make possible a statutory safety assessment, which has to be carried out every 6 years, based on maximum allowable probabilities of failure. And it says 2017 because by that time the project has to be finished. Well, one way, of course, to evaluate whether we meet a certain maximum failure probability would be to carry out a probabilistic assessment, to calculate a failure probability. I see it moves a little, but in a probabilistic assessment, we're basically looking at the probability that load exceeds resistance. Because if the load exceeds the strength of the levee, it will fail. And for that, of course, we need probability distributions for load and strength variables. Another way to assess whether a levee is sufficiently safe would be to carry out a semi-probabilistic assessment. And in a semi-probabilistic assessment, we use design values. And we're asking ourselves, is the design value of the load greater than the design value of strength? And a design value is a unique value out of an entire probability distribution. And for that reason, quite often engineers call those types of semi-probabilistic assessments deterministic assessments. Well, I think that terminology is slightly confusing because the exact same uncertainties play a role in probabilistic assessments. Well, of course, the tricky part is how should we define such design values? And ultimately, basically, the idea is that these design values should be chosen in such a manner that if this criterion is fulfilled, the probability of failure is sufficiently low. And this procedure of deciding on design values is also called a calibration process, a calibration exercise. And before I continue, I think it's useful to introduce you to some basic terminology. A design value is a representative value divided or multiplied with a safety factor. And a representative value is, for instance, a 5% quantile value, a 95% quantile value, or, for instance, a 1 in 10,000 year quantile value, such as a 1 in 10,000 year water level. Because of the role of safety factors, I will from now be mostly talking about the calibration of safety factors rather than calibrating design values. The procedure that we developed within the context of the WTI project is first to establish a reliability requirement, then to establish a test set, which is basically a large number of levee cross-sections, then to modify these test members, the test set members, according to the semi-probabilistic rule for a range of values of the safety factors that we chose to include in this rule. So then we end up with a whole range of test set members that are modified. Then we're going to calculate a failure probability or a reliability index for each of these test set members. And then finally, we're going to select an appropriate safety factor based on the outcomes of all these calculations. And I will now explain to you what this actually means via a case study. And our case study that I'll be presenting here concerns piping. This is a failure mechanism whereby internal erosion causes a pipe to grow underneath the levee. And this could eventually lead to, progressive erosion could eventually lead to collapse of the levee. The rule that we considered for describing the strength or the resistance of a levee against piping is the so-called Selmayr equation, which is used in the Netherlands in our statutory assessments. And what I would like to emphasize is that the results that I will be presenting here are the results of a preliminary calibration exercise that was mostly aimed at optimizing our methodology. Well, the first step is to establish a reliability requirement, which has to be specific for the failure mechanism under consideration. And there are many failure mechanisms that could trigger flooding. There are many failure mechanisms that could cause the failure of a levee. So what we do basically is distribute this maximum allowable probability of failure over the different failure mechanisms. And in this preliminary exercise, we allocated a slot of 35% to piping. So if the maximum allowable failure probability is 1 in 10,000, then the reliability requirement for piping is 35% of 1 in 10,000. A second step is to establish a test set, basically a whole bunch of cross-sections. And these were taken from the VNK2 project, which is a large-scale risk analysis for all Dutch major levee systems. And I'll be giving you a presentation about that tomorrow. So please feel free to come and see. A third step is to modify each test set member according to different values of the safety factor. So if we apply a higher safety factor, the levee has to be stronger. Its resistance against piping has to be greater. And this could, for instance, be done by adding a berm to increase the seepage length, the length of the seepage path. Well, and the higher the safety factor, the greater the safety factor, the greater this berm should be. A fourth step is to calculate failure probabilities or reliability indices for these different test set members. And what you will see is that the higher the reliability, the higher the safety factor, the higher the reliability index will be. And here you see some of the results of the calculations that we carried out. On the vertical axis we've got the safety factor, and on the horizontal axis we've got the reliability index. And each dot is a different modified test case. And from such a graph we could, for instance, see if we choose a certain safety factor, what the corresponding betas or failure probabilities would be. We could also move in the opposite direction and, for instance, select a target beta and then see what the corresponding safety factor would be. Well, a fifth step is to apply a calibration criterion to select the safety factor, because it would be overly conservative if we would say that every test case has to meet a certain probability requirement, because there's always some averaging out going on. So here on the vertical axis we've got the average cross-sectional failure probability divided by some target failure probability that was assigned to that value. So if this ratio is equal to 1, you could say that the safety factor is not overly conservative and is not too optimistic. So in this case, for our case study, a safety factor of around 1.2 would seem appropriate. So some concluding remarks. This calibration exercise, this calibration procedure that we developed appears to be broadly applicable. So far we've tested it for piping, for wave overtopping, slope stability, non-closure and structural failure. And what we found is that the use of such a standard procedure not only contributes to the efficiency of calibrating design values, but it also contributes to transparency and to consistency. And not only to the consistency between different failure mechanisms, the way we treat different failure mechanisms, but also to the consistency between failure probability calculations and semi-probabilistic assessments. And finally, what we found is that these preliminary calibration exercise provides some early insight into the likely outcomes of the new types of statutory safety assessments if we would keep using the present-day models, statistics, etc. that we have. And this can also be a major drive for further research. And with that, I'd like to end my presentation. So if you have any questions, please do not hesitate to ask or contact me.
Thank you very much indeed. Ruben, I would just like to ask a first question, if I may, because I think it's really important one, which is that we have moved in Europe to Eurocodes, and within Eurocodes we have partial safety factors in a similar way that you've just described in your presentation.
Yeah.
There is concern in some areas about the fact that those safety factors may lead to overly conservative designs. Do you think that your research will be able to contribute to answering those questions?
This is actually a very good point, because this is also a part of an ongoing debate in the Netherlands to make sure that there's some consistency with the Eurocode system. So we also look at what the Eurocode prescribes, what the ideas are behind those safety factors, and basically use standardized form influence coefficients, for instance, if you want to derive safety factors. One of the reasons why we chose for this calibration exercise is that in the new statutory assessments, we will also always allow people to also make a probabilistic assessment. So what we want to ensure is that the gap between semi-probabilistic and fully probabilistic assessments will be as small as possible to make this a very useful method to apply. And that means that sometimes we have to move away from certain factors that are used in the Eurocode system. Also, by the way, because the target reliabilities might be different.
Okay. I've got time for one more question, perhaps.
Yeah, just a quick question. Could you try and clarify the reason for adopting a semi-probabilistic approach as opposed to a fully probabilistic approach? What's the main motivation for that?
Well, the main motivation is that basically our current methods are semi-probabilistic methods. And if we would directly move away from the methods that everyone is familiar with, we would just encounter huge problems. So that's basically the main idea. Also, probably because these methods are easier to apply, so that could be an advantage in our statutory assessments, that people start, for instance, with these types of assessments, and from there they could decide if they want to move to a higher level and carry out a probabilistic analysis.
Okay, one last quick question.
Why did you choose 35% as part of the total failure for piping? Why not 5% or 50%?
Yeah, well, that's a good question. That's part of the things that we'll be reviewing in the next few years. But what we've seen recently in the VNK2 project, for instance, is that the contribution of piping to the overall probability of failure is likely to be a lot higher than 5%. And if we were to choose 5%, that basically means that these safety factors would be relatively stringent. And that would create sort of a mismatch between what you would expect from a semi-probabilistic assessment and a probabilistic assessment. I think it ties in nicely with the talk by the gentleman from the US Army Corps of Engineers that also said that for them piping was a relatively important failure mechanism. And if that's the case, I think assigning a value of only 5% will lead to, well, excessively conservative semi-probabilistic assessment rules, so relatively high safety factors.
I'm sorry, we're out of time for questions, but please, it's an interesting presentation, so please feel free to talk to Ruben after the session is over. Okay.